Dear students, in this module, you will learn about the valence bond approach of inert and labile complexes. After learning this module, you should be able to understand about inert and labile complexes, cause of lability and inertness by virtue of valence bond theory, and the limitations of explanation of lability and inertness provided by the valence bond theory. So, before proceeding for the lability and inertness, we should first go towards the definition of them. So, let us define about inert and labile complexes. Under the fixed condition of concentration of substrate of 0.1 molar and temperature 25 degrees centigrade, complexes that undergo quick displacement of one ligand by the other are called labile complex. By the term quick displacement, we mean to say the half-life time of the displacement reaction should be lower than that of 1 minute. While in a complex in which ligand displacement or substitution process is slow or slower to this 1 minute half-life time process is called the inert complex. The schematic diagram for the reaction is shown here, in which ln mx is when reacted with y was substituted in place of x, and this reaction was called displacement reaction. The example for the same is when hexa aqua iron third complex was reacted with thiocyanate ligand, water molecule get easily displaced and a complex FeH2O whole 5 HCl second plus used to form with removal of a water molecule. Substitution of HCl minus in place of water in the above shown example is very fast and generally used to complete within a minute, and therefore the complex FeH2O whole 3 means hexa aqua iron third complex is called a labile complex. Term inert doesn't mean that the displacement reaction is not possible or substrate doesn't allow any kind of substitution reaction. Instead, it is a comparative term which is used here to represent a comparatively slow reaction. The term lability and inertness is not related with the thermodynamic stability of the complex and are purely kinetic terms. For example, tetracyanonickel second complex is thermodynamically stable. As you know, cyanide ion is a strong ligand, but the complex is labile in nature and get quickly exchanged by the cyanide ion, in which carbon was having mass number 14. Cause of lability and inertness was explained by different theories, but we are here learn about the valence bond theory approach for the lability and inertness. Now, in the very first point of this section is high spin complexes are labile and undergo dissociative SN1 reaction. We need a little bit explanation about this. Since in case of high spin complexes, the ligands are more distant situated from the nuclei of central metal ion, and the hybridized orbitals are high energetic. As a result of these causes, breaking of metal-ligand bond would be easier and displacement reaction will follow dissociative nucleophilic substitution reaction pathways. In the example, thiocyanate ion displaces a water molecule. The magnetic moment for FeH2O whole 6 2 plus was found to be 4.9 Bohr magneton. Iron in FeH2O whole 6 2 plus has coordination number 6 and oxidation number 2. So, if you see the orbital picture of iron in FeH2O whole 6 2 plus, you can have the picture. From the magnetic moment value, it is clear that total number of unpaired electron in the complex is 4. That you can see by the formula As you know, spin only magnetic moment value found out by the formula root under n into n plus 2 Bohr magneton, where n is the number of unpaired electrons. So when you represent, or when you find value of n from the value of magnetic moment that we obtain for hexa aqua iron second complex, then n we find is 4. So after approach of 6 water molecule, iron second plus used to hybridize 6 of its lowest energy orbital possible, and those 6 orbitals are 1 4s orbital, 3 4p orbital and 2 4d orbital. All the 6 orbitals combine or hybridize to form 6 equal energy sp3d2 hybridized orbitals. So before complexation, 1 4s, 3 4p, 2 4d orbital hybridized and provide 6 sp3d2 hybridized orbitals, in which every water ligand provides a pair of electrons. Therefore, all orbitals that participate in the bonding are of high energy and are distant from the nucleus. Because of high energy of bonding orbital, these bonds require lower amount of activation energy, as reactant molecule itself has high energy and therefore breaks before the approach of attacking ligand. Less attractive forces from nuclei of metal ion also supports the dissociative mechanism. What we get in case of high spin complexes, dissociative, that is SN1 mechanism is favorable in case of displacement reaction. Now we come towards the second point head, and that point head says about a low spin complex are labile but prefer associative mechanism. Since a bond closer to nuclei is more stable and stronger, therefore inner orbital complexes that has hybridization n-1d2 sp3 for octahedral and n-1d sp2 for square planar would not prefer dissociative mechanism. As you can understand, because of stronger bond, the breaking of bond in the first step would be difficult. So complexes in such cases are inert in nature for dissociative kind of reaction. On the other hand, an associative mechanism involves attachment of an attacking ligand before removal of leaving group. This kind of mechanism is favorable with inner orbital complex, as the molecule doesn't allow removal of leaving group before attack of incoming ligand. For example, when hexacarbonyl cobalt 3+ is attacked by a labeled carbon monoxide ligand, then displacement reaction takes place through associative nucleophilic substitution reaction only, and dissociative mechanism doesn't take place in this example. If you see the orbital picture of cobalt 3+ in the ground state, you can see, and no ligand was attached over it, it is having 6 electrons in its outermost shell. So the 3d orbital will occupy or will contain 6 electrons as shown in the diagram. Now if we find the magnetic moment for the complex COCO6 3+, then we find the magnetic moment of the complex is 0, that is the molecule is diamagnetic in nature. So in the complex form, that is in the excited state, the orbital picture would be like all the 6 electrons of the 3d orbital will be filled in the first 3 orbitals of the 3d orbitals, and rest 2 orbital would be free. And to occupy 6 electron pair provided by 6 carbon monoxide ligand, we can have 6 free orbitals. So after first 3 3d orbitals, the hybridization of the 6 metal orbital would be like 2 3d, 1 4s, 3 4p orbital will combine to provide a hybridization of D2sp3. The two 3d, 1,4s and 3,4p orbital hybridized to provide 6 D2sp3 orbitals of equal energy. These 6 orbitals are the lowest possible unoccupied orbitals and close to the nucleus. As a result of these two facts, bond between metal and ligand are strong enough and therefore difficult to break. The complex will therefore prefer associative mechanism because before dissociation of CO-CO, attacking ligand will join to form a transition state. So in case of low spin complex, the compound will prefer an associative mechanism in place of dissociative. Now let's move towards the next point here. Complexes that contain at least one vacant d orbital prefer associative mechanism. Let's illustrate this point. Complexes containing metal ion having fewer than 3 electrons in their d orbitals have no clear-cut distinction from valence bond theory. Means in both the cases, in either in high spin complex or in low spin complex, in both the cases electron filling and the free orbitals would be same. So there is no clear-cut distinction by the above 2 point heads that which mechanism preferable for the dissociative kind of displacement reaction. Complexes containing metal ions having fewer than 3 electrons in their d orbitals have no clear-cut distinction from valence bond theory about whether the reaction will go through high spin complex or low spin complexation. Such complexes are having good chances to accept a pair of electrons provided by the attacking ligand in the vacant first 3 d orbitals and that are empty even after hybridization. Examples are octahedral complexes of scandium 3+, titanium 3+, vanadium 4+, yttrium 3+, etc. They all prefer to accept an electron pair from the attacking ligand and therefore prefer to undergo associative mechanism. On the other hand, substrate in which metal ions that at least have first 3 d orbitals in its own by its own electrons, that is configuration of metal ions should be from d3 to d6, will direct incoming ligand to outer d orbitals and therefore associative mechanism are less favorable or complexes are inert for associative substitution reaction. Although valence bond theory explained lability and inertness complex in a quite good manner, but still it has the limitation. So let's learn about the limitation of the valence bond theory. Although the theory is simple to understand and explain most of the observation of labile and inert complexes satisfactorily, but exception exists, and the exception is in case of D8 configuration of metal ion, incoming ligand has only chance to occupy outer d orbitals and associative substitution reaction should be less favorable. But experimentally such compounds were found labile for an associative reaction. Also, the valence bond theory has only the qualitative reasoning for the inertness and lability of the complexes and no quantitative aspect was discussed by this theory. So these are the two major limitations for the valence bond theory. Let's summarize the whole learning. Complexes which undergo fast nucleophilic substitution reaction are called labile. By the term fast, we mean to say T half, that is half lifetime of reaction, should be less than 1 minute. Complexes which undergo slow nucleophilic substitutions where T half is greater than 1 minute are called inert. Conventional theory cannot give clear-cut reason about lability and inertness of the complexes. According to valence bond theory, high spin complexes are labile and undergo dissociative acid-1 reaction. A low spin complexes are labile when undergo associative mechanism. Complexes containing metal ions having one empty inner d orbital prefers associative mechanism of nucleophilic substitution reaction. And complexes in which metal ion that at least have first 3d orbital by its own electron is filled will direct incoming ligand to outer d orbital, and therefore associative mechanism would be less favorable. So that's all about the module.